All right, today we are finally officially starting chapter 5. We are going to be identifying quadratic functions and their graphs. All right, we've got standard form of a quadratic function or quadratic equation. It will be ax squared plus bx plus c. A quadratic must have a squared term called the quadratic term. I know that's cut off. I'll go over what it says in just a minute. A quadratic must have a squared term, which we call the quadratic term. It does not necessarily need the linear term or the constant term. So it says it does not necessarily need the linear term or the constant term. Those are the last two blanks right there. Does not necessarily need the linear term or the constant. Okay. We are going to determine whether each function is linear or quadratic, and then identify the quadratic, linear, and constant terms. It says we may need to simplify the expression first. So our first problem says y equals the quantity 2x plus 3 times the quantity x minus 4. And we are given this friendly reminder, FOIL. Does anyone remember what FOIL stood for? We've never heard of that?
I've heard of it, I just can't remember what it is.
So when we multiply two binomials together, FOIL, it's kind of an outdated way of being taught it. It's how I was taught it many, many years ago. It stands for first, outer, inner, last. So it's first, outer, inner, last. It's not what we're learning today, and it's not the only way to do these. I think now the preferred method is to double distribute. So we distribute the 2x to both terms in the second set of parentheses. We distribute the 3 to both terms in the second set of parentheses. The first, outer, inner, last refers to multiplying the first terms together, the outside or outer terms together, the inside terms together, and then the last terms together. It's the same thing either way. We're multiplying these two binomials together. When we do that, we would get 2x times x. What would that give us? 2x squared. This is why we reviewed our exponent rules. 2x times a negative 4 is negative 8x. 3 times x is a positive 3x. And 3 times negative 4 is negative 12. And then we would want to simplify that. So, what can be simplified there? Good. The x terms. Negative 8x plus 3x gives us negative 5x.
Why don't you go like negative 12, no, 2x squared minus 5x minus 12, like that order?
Yes, that is the order we have it in. That is the order we want it in. That's why on the last slide we said standard form is ax squared minus bx or plus bx plus c, right? The constant comes last. Now that we have simplified this, we can decide whether or not it's a quadratic. And we kind of gave the answer away already, but does this fit the quadratic standard form from the last slide? Yes, it's got a squared term. It has to have a squared term to be a quadratic. So yes, this would be a quadratic. And then we have to identify the quadratic, linear, and constant terms. So, looking at our simplified version, can anyone tell me what the quadratic term is? Jacob. 2x squared. So this is my quadratic term. What is my linear term? Negative 5x is my linear term. And what is my constant? Negative 12 is my constant. I'm running out of room. On we go. So that second problem, I'm going to erase part of the top of the screen so that I can rewrite it up at the top. We'll follow those same directions, but it's hard to work with it all the way at the bottom there. But it says that f of x is equal to 3 times x squared minus 2x minus 3 times x squared minus 2. If it's hard to see that at the bottom, that's what it says. Now we need to simplify this. We're not going to FOIL on this one necessarily, but we still can simplify it. We've got to distribute. So when we distribute this 3 out in the very front, what do we get?
3x squared minus 6x.
Wonderful. And then we distribute a negative 3 to the second set of parentheses.
Negative 3x squared plus 6.
Beautiful. Questions on how we got that far? All right. Then what can we do?
Add the 3x squared. Well, they cancel out.
They cancel out. We're combining like terms, but we notice a positive 3x squared and a negative 3x squared cancel each other out. Can we combine what's left? Nope. So we're going to leave it negative 6x plus 6. Is this a quadratic function?
No.
Why not?
Because it doesn't have a square.
Very good. There is no squared term. So this one is not quadratic. We still have a linear and a constant term, though. What term is linear?
Negative 6x.
The negative 6x is still considered a linear term. And which one is constant?
6.
The 6 is a constant term. If the directions ask us to, we should. Questions, concerns about identifying a quadratic versus a not quadratic function? Okay, let's move on and talk about everyone's favorite thing, graphs. Don't boo. I like graphs of quadratics. The graph of a quadratic function is a parabola. It looks like a U, a capital U. The graph of a quadratic function is a parabola. It looks like a U. Each has an axis of symmetry which divides the parabola into 2 parts that are mirror images of each other. It's always a vertical line with equation x equals a number. The vertex of a parabola is the highest or lowest point when the parabola intersects the axis of symmetry. So we have to get all this kind of vocab stuff down, but then we'll see it in action when we look at a couple graphs coming up here soon. Now that we've got our graph drawn in, we have to identify the vertex, the axis of symmetry, and the points corresponding to P and Q. I'll go ahead and tell you. Down here is where we've got point P, and up here is where we've got point Q. But we'll get to those in just a moment. First, we want the vertex. On the last slide, we talked about the fact that the vertex is the highest or lowest point, depending on what our parabola looks like. Lanaya, do you think you know what it is? 2, 0. Our lowest point of our graph is going to be at 2, 0. will there be a highest point of this graph? No, it keeps going up and up and up and up and up. Okay, so our vertex for this problem is going to be at the point 2, 0. Your vertex should be written as a point, just like when we did do absolute value. Eventually, we will see parabolas flipped upside down, where they will have a highest point, but not a lowest point. Next, we need to talk about our axis of symmetry. Now, if I had drawn my parabola a little bit prettier, it would be easier to see it. But your axis of symmetry is a vertical line, and it's going to go through your vertex. So I can go ahead and sketch it in. We use a dotted line for our axis of symmetry because it's not part of our graph per se. It's not part of the graph of this line. It's just a feature that we use to help us understand the graph. That axis of symmetry, we'll often refer to as AOS, has an equation of the form x equals a number. That was also on our last slide. In this case, x is going to equal 2, the x coordinate from your vertex. It goes through that same point. X equals 2. Finally, we are asked for P prime and Q prime. These are going to be points. If I labeled P, point P, as being at 1, 2, P prime is the mirror image of that on the other side of my axis of symmetry. What point is that? 3, 2. So over here is where I would find P prime. All right, we're asked to do the same thing with point Q. So where is Q prime? Oh, I lied to you. That's why this looked wrong. It shouldn't be at 3, 8. It should be over one more space. No wonder that looked so off. All right, so it should be over. If Q is 2 away from our axis of symmetry, then Q prime should be 2 away. So if I go 2 more, what's it really at? 4, 8. That's why that looked so funny. Okay. So Q prime is going to be at the point 4, 8. Any point along your parabola should be equidistant from another point on the parabola. So we should be able to do that with any point we choose on either side of it. Obviously, there's no reflection of the vertex. It is on the axis of symmetry. Once again, it would have been helpful if the graph had been printed on here already, but since it was not, I will sketch it in. For this function, y equals x squared minus 6x plus 11, our vertex is at 3, 2. All right. So our vertex is going to be down here. Well, I already told you, kind of gave that away. That's our vertex. We've got a point there. We're going to have a point. Point P is going to be at 1, 6. And so I'll label that point P over there. Point Q is going to be at 4, 3. Those are going to be the only points we start with. So I told you this is our vertex so that you'll know that that's where your U comes out of. So it's not necessarily going to be perfect, but we can get it kind of close. It's not close enough for me. All right. That's better. And there. Okay. All right, when we identify our vertex, we look for the highest or lowest point. So I kind of already gave it away. Where's our vertex? 3, 2. That's the lowest point. Our axis of symmetry is going to be a vertical line. Where is it going to go? What point does it have to go through? 3, 2. It has to go through our vertex. So we are going to put a dotted line vertically through our vertex. But we need the equation of that line. Vertical lines are always x equals, so in this case x is going to equal 3. Alright, finally we want to identify what P prime and Q prime should be. I have not plotted those points yet at all. We are going to have to find them using our axis of symmetry. So if we start at point P, how many spaces horizontally from our axis of symmetry is point P? 2, right? We go 1, 2 spaces over. So we need to go 2 more spaces, continuing on in the other direction. 1, 2, and that's where our point should be for P prime. What are the coordinates of that point? 5, 6. I would agree with that. So P prime is going to be at 5, 6. Okay, we do the same thing for Q to get to Q prime. How many spaces away is Q from our axis? 1. So we go 1 more the other way. We put a point there. What point is that?
2, 3.
2, 3. So Q prime is at 2, 3. What questions do we have? Nothing? Alright, today's notes were pretty short and sweet.